this recitation activity, but I'm going to kind of work through a video that you guys can use to perhaps do this activity from home and to hopefully better understand the answers if you're looking at this after recitation during the week that we do this activity in class. Okay, so for this question here, we're looking at the A versus the B constants in the van der Waals equation. I think the idea would be that we'll give you, or you can look at this equation where you have, and you don't have to have this equation memorized, but it looks something like this. Know that you can see this equation so that you can look at B as the constant that's fixing the free space issue due to the space occupied by matter. So B is directly proportional to the size of the particles. So how much of the gas, how much volume the actual matter of the gas is taking up in the container. So we can plug in and really plug in the free space volume here, as opposed to the container volume that we usually use with the ideal gas law. So it's fixing the issue of how much space is actually occupied by the matter. And then the A constant is fixing the pressure that we lose due to intermolecular forces. So A is directly proportional to intermolecular forces. And they have opposite impacts. So the free space volume is reducing the volume, but then the intermolecular forces are taking away some of the moles of our gas. We have to sort of add some of those particles back in to get a better description. And so A is directly proportional to the strengths of intermolecular forces. We'll talk about those more in chapter 11, and then particle size for the B constant. Following back in the video here. So the B is directly proportional to particle size. So which of the following properties of a real gas is related to the definition of the B constant? So real gases consist of atoms which have a finite volume of the container. So that sounds like the actual statement of what the B value is. The average speed of molecules of a real gas increases with temperature. That's a true statement, but not anything to do with the B constant. There are attractive forces between atoms or molecules in a real gas. That's a description of the A constant, not the B constant, so that's not the correct statement. The rate of diffusion of a gas is inversely proportional to the square root of the molar mass of the gas. That's a true statement, but not for the B constant. So the correct statement here, well, I guess I wasn't going to give the answer, but I just did. But so the answer to this question would be A. Answer to the questions as we go along, just so that you guys can make sure to think through the problem. But ranking the following substances in order of increasing boiling points. So I'm looking at these molecules here. These are all either nonpolar or very close to nonpolar molecules. So the key is which of them have a larger sort of volume of space that they're occupying. And so a single atom, and another thing I might take note of is I have a C3, so 4, 5, 6. So I have a C6H9, 10, 11, 14, C6H14 isomer here, and then this is a CH3, so then a CH2. Counting my carbons right here, 1, 2, 3, 4, 5, 6. I'm going to edit this to be a 4 when I put this up online. Change it before you guys get a chance to do this, because I meant for this to be a C6H14 isomer as well, so that we're kind of comparing molecules that are either branched hydrocarbons or straight chain hydrocarbons, but they're both of the same formula, so they're isomeric to each other. And so then if we also then think of the relative molar mass, that's like 72 plus 14, so we're talking about 86 grams per mole. Cl2 is about 71 grams per mole, krypton's about 80 grams per mole. So we're kind of comparing molecules that are similar size, all nonpolar. So the question is, which of these molecules is either the most or the least polarizable, or the easiest for the electrons to induce a dipole moment? Let's think about the hardest. So if I have a single sphere of this mass of about 80 grams per mole, there's such little contact between a second sphere that it's really hard to induce this dipole moment when we just have one atom. It's a little bit easier when I have two atoms. It's even easier when I have a bunch of atoms like I have in the C6H14 isomers. And then it's going to be easier when the hydrocarbon straight chain, one, two, three, four, five, six, versus when it has one of these branching points in the structure. So if I have a branching point in the structure, it kind of kinks the structure. If you imagine two of these molecules side by side and their CH3 groups hanging off of these positions here, it's going to be harder for that branch structure. It kind of makes it look more like krypton in a way, where there's less contact points. What we want is a long chain or a bunch of atoms so that we get an easy ability of two molecules that are like, adjacent to each other to be able to induce a dipole moment in themselves. And so the more atoms, the better for increasing the strengths of intermolecular attraction. So we're going to increase boiling points. It's going to take more energy to separate our molecules into their gas state when we have stronger intermolecular forces. So the higher the intermolecular force strengths, the higher the boiling point. So we should get the higher intermolecular forces for the straighter chain hydrocarbons and for having more atoms. I'll let you guys piece it together from there. At this to make sure that we're looking at isomeric structures here in the case of those hydrocarbons. Boiling point of CH2Br2 is 97 degrees C, while if we have a third bromine is 149 degrees C. So what do we think is most responsible for this difference? Now, bromine is relatively electronegative. It's not the most electronegative element. It's not as electronegative as, say, the chlorine atom or the fluorine. So, but it's relatively big. So having a third bromine adds a lot of mass. We're adding about 80 grams per mole when we add that third bromine to this compound. And so the primary factor, I would say, like if we're looking at our sort of a Lewis structure here, might be I have two bromines for the one structure, I have two hydrogens for the other. If I add a third bromine to the mix, I'm thinking about picturing a bromine here, that I'm not really making the compound that much different in its polarity, but what I'm really doing is I'm changing the mass. I'm adding a lot more dispersion forces by having a bigger bromine in the case of CHBr3. So the explanation for the difference of these boiling points, I think, is going to be the London dispersion force is going to be much higher because I have that third bromine to give me greater dispersion forces. The dipole-dipole force, I don't expect that to be very different by adding a third bromine. Both compounds are polar. I don't think one is so much more polar than the other. None of these compounds form hydrogen bonds. The covalent bonding has nothing to do with the boiling points because we're not breaking any of the bonds in a molecule. So like these bonds here don't break when we boil a substance. We're just breaking the intermolecular forces between an adjacent. So the force we're breaking is the forces between an adjacent molecule, attractions between molecules that we're breaking when we boil a substance. And so we're just going to be increasing the dispersion force with that third bromine on CHBr3. Number 4, in its liquid state, which type of intermolecular forces does ClF5 contain? And so we're even told the molecular geometry is square pyramidal. Well, let's make sure that we understand where that's coming from. ClF5 would have 7 times 6, that's 42 valence electrons. So a central chlorine with 5 fluorines will look something like this. Electron pairs around each of the F take 40 of the electrons, leaving 2 electrons behind, which I can put sort of downward here. So I get this square pyramidal structure. And this molecule here, the key is seeing that it is polar because of this electron pair and where it is in the molecule, giving us an imbalance in a net dipole moment pointing straight up towards the electronegative fluorine. And so what type of intermolecular forces do we have in this compound? Well, I should definitely have dispersion forces, and then I should also have dipole-dipole forces because the compound's polar, has the dipole-dipole force, and everything has dispersion forces. And so I'm going to have both A and B, and then I don't have ion dipole forces because I would have to have an ion somewhere. An ion dipole force is the force of attraction between like sodium and like a water molecule. So this attractive force here, this is an ion dipole force, nothing like we see in ClF5 as an ion dipole force. And there's no H bond force of attraction either. So I need hydrogen directly attached to NO or F to have a hydrogen bond. So I don't have hydrogen. It's not part of the question, but I don't have those either. Which substances below, or excuse me, the substances below have molar masses that are within about 2 grams per mole of each other. So which substance has the lowest boiling point? We're being told this just so that we can see that there's really no great difference in dispersion force between these compounds. The key is going to be the one that has the overall least polarity. So if I'm looking at some of these molecules that are going to have dispersion, they all have dispersion forces, but they're going to be relatively comparable for all these molecules. If a molecule has dipole-dipole forces, that will increase its attractive force. And if we have H bonding forces, that'll increase it even more. So the highest boiling is likely going to be C because it's the only compound that has H directly attached to O. So this has all three of those intermolecular forces. So this probably has the highest overall boiling point. I then have these two compounds here, which I might have a hard time choosing which one has the greater dipole moment. But these are both polar, but not able to form H bonds, so these are probably in the middle. Then I have C at the highest, and I have B and D somewhere in the middle. Then my lowest is going to be A because I don't have a polar atom, so I really don't have a great polarity difference, and I have a lot of the same atoms, so just the geometry kind of compels the structure to be fairly nonpolar. So we have a nonpolar molecule here. So A is going to have the lowest boiling point, C would have the highest, B and D somewhere in the middle. It turns out I think it would go B lower than D. I don't know if we'd expect you to know this, but this carbonyl group is relatively polar. You'll see that a lot in OChem. So you'll see that this molecule here is pretty polar in the case of having that carbonyl. I'd expect you to make this trend here. Question. The molecules in pure liquid dichloromethane CH2Cl2 experience which of the following intermolecular forces? Another thought could be if you're going to boil this substance, if you're going to evaporate the substance, which forces have to be overcome in order for this substance to vaporize? And the answer is going to be you have to break the dispersion forces, the dipole-dipole forces, so let's put check marks there, but not the H bonding force of attraction. So I have, of course, in this compound, the carbon-hydrogen covalent bond, but that's not what a hydrogen bonding force of attraction is. A hydrogen bonding force of attraction is when H is directly attached to O, to N, or to F. And we get that especially strong attractive force between neighboring molecules. So this is the H bonding force of attraction. Between neighboring molecules is the H bond. And you need hydrogen directly attached to those atoms in order to have the hydrogen bonding force of attraction. So no hydrogen bonds possible for number 6. The following molecules can form intermolecular hydrogen bonds. So just remember, hydrogen bonds are what we call the intermolecular force between molecules. So if I'm looking at these molecules here, H directly attached to O, so that's good. I see fluorine, but I need H directly attached to fluorine because fluorine only forms one bond commonly. We don't see fluorine bridging to make two different bonds. It's going to be pretty much the case that the only fluorine-containing molecule that can H bond is HF. So we don't get H bonds here. We have hydrogen directly attached to a nitrogen, so that looks good for hydrogen bonding force of attraction. In the thiol, we have H directly attached to sulfur. Sulfur is relatively electronegative, but unfortunately it's just too big to give this molecule any especially strong attractive force of attraction. So generally speaking, we're not going to say that this SH bond is capable of forming that intermolecular hydrogen bond. So notice that the hydrogen bonding force of attraction has nothing to do with just having covalent bonds involving hydrogen. It has all to do with a molecule that has a covalent bond between NO and F and H, such that the adjacent molecules of those samples, of those molecules in the liquid, can experience that intermolecular force of attraction. Question 8, the critical point 2 is 304 and 73 ATM. Now, the critical point in terms of thinking of a phase diagram, kind of goes like this, where you have your solid phase, your liquid phase, and then your gas phase. And this is your critical point here, where if you go to a higher temperature or pressure, then we call that a supercritical fluid in terms of the best description of the state of that substance. And so if you're above both the critical temperature and pressure, then you would be in the supercritical fluid state. But if you're, say, and let me also define one of these axes to be pressure, one of these to be temperature. But if you're, say, above the critical point temperature but below the critical point pressure, then you're still a gas, like you're over here in the diagram. But if you're above the pressure and temperature critical point, then you're in that supercritical region over here. And so let's take a look at some of the temperature conditions here. So if we're at 303 and 73, that's still, so if we're at a lower temperature, so we go over to here, we go to a lower temperature but at the critical point, then that's going to put us into the liquid phase. And then if we are above each of those points, then we are in the supercritical fluid stage. So the statement 2 here is a supercritical fluid. At condition 1 is just we're still in the ordinary liquid phase. If we, because again, we're right at the critical pressure, right below the critical pressure, we go into the liquid phase. A phase diagram. So we're looking at a phase diagram of elemental sulfur. Which statement is correct about sulfur? So we see a couple different solid forms here. So we see solid form 1, solid form 2. There's a liquid state. And we have gaseous states. We have a couple points marked here. This is our triple point, the coexistence of our 3 phases. And this point here is, or I'm sorry, we actually get 2 different triple points. We get a triple point between, or it's, I guess, a quadruple point between 2 different phases of a solid and then the gas phase. And then we get this point here between the gas, liquid, and one of the other solid phases. And so let's see, rhombic sulfur cannot be sublimed without first converting to monocyclic sulfur. And so what this means, if this statement saying sublimation would occur in this region here because it's the direct transformation of solid to gas. And so for rhombic sulfur to sublime, it's going to go below the triple point there. So rhombic sulfur can indeed sublime without first converting to monocyclic sulfur. So at low enough pressures, it can indeed interconvert to a gas directly without involving the monocyclic sulfur or whatever that is, monoclinic sulfur. The conversion of rhombic sulfur to monoclinic sulfur is exothermic. Let's think about that transition here. So temperature, so to go from rhombic to the monoclinic involves temperature increasing. So energy has to be absorbed by the process. So this is kind of the whole idea that ice to liquid water needs to absorb energy, and that would be endothermic. So this process here is endothermic. So rhombic to monoclinic, needing to absorb temperature to take place, should be endothermic. So I don't think that statement is true. Rhombic sulfur is denser than monoclinic sulfur. And so, okay, how does density apply? Well, imagine we have the monoclinic here, so we have this solid at this point in our diagram. If we apply pressure and increase pressure, then we go upward in our diagram. And so increasing pressure is another way of increasing the density because you're pushing the atoms to be closer together. So by adding pressure to a substance is the act of increasing the density of a substance. And so if we increase the pressure of rhombic sulfur, we increase its density. And if we take monoclinic sulfur and increase pressure onto it, we increase its density. We then have it change form at some point when we apply enough pressure into rhombic sulfur. So rhombic sulfur indeed is denser than monoclinic sulfur. So I believe this statement is true. And let's make sure, hopefully statement D is false. So at atmospheric pressure, monoclinic sulfur cannot be in equilibrium with liquid sulfur. And so one here, so that's standard atmospheric pressure. So I would almost rather say at standard atmospheric pressure, but I think that's what they're trying to imply. So at standard atmospheric pressure, monoclinic can indeed be in equilibrium with the liquid phase here because we see a transition from the one state to the other. So this is not a true statement. This is a tricky question. I've actually never seen this question here before. Question 9, this is the first time I've ever seen this one. So this is probably a little bit trickier than I would anticipate for our exam. I took this off of an old Olympiad practice exam that they have up on the internet that has like some phase diagram questions, just so we can see a question like this. So pretty complex question here for question 9, but just something that gets us to think about relative phase transitions. Gets us to think a little bit about how like ice needs to absorb heat to melt, so that's endothermic. And so then rhombic sulfur needs to absorb heat, needs to increase its temperature in order to change form into monoclinic. So therefore that also is endothermic. So at least gets us back into thinking of some phase change values from chapter 5. All right, that's it for this video. Thank you for listening or watching.